right, so here's problem number 37 from section 3.4. Okay, so we're given that the x-coordinate of a particle moving on the line y equals 2 is given by this. So imagine, of course, here's our axes, and it just so happens that this particle always moves on this line back and forth on this line y equal 2. And the x part of this coordinate is determined by the expression x sub t, blah, blah, blah. All right. Describe the motion of the particle when t is greater than 0. So the question is, well, what would that be? Well, I think I'd like to describe. There's only two things that this particle could be doing. Well, three things. It could be going to the right. It could be going to the left, or it could be standing still. So let's see if we can discover what's going on with this particle motion. So in part A, I'm interested in taking the derivative of our position equation and getting the velocity. All right? So when I do that, I get 6t squared minus 26t plus 22. Are you okay with that?
Yeah.
All right. My next question then is, are there any zeros here? Let me factor out a 3. No, not a 3, a 2. See if makes our lives a little bit easier. 3t squared minus 13t plus 11. So I'm looking for a way of factoring this so that 30. Now that doesn't look like it factors at all.
Yeah. So
Does it not factor?
No, in your video, like I watched the video.
Oh wait.
Do I already make a video of this?
Yeah,
Yeah.
like I watched it and it made sense to me.
Tomatoes. Okay. Well, I'm interested in, are there places where the particle is standing still?
So when velocity is 0.
So if I'm going to use what? Maybe I'll use the quadratic formula for this.
Yeah.
Find. Okay.
Yeah.
And so
that's
minus
easy.
b minus a minus 13 plus or minus the square root of b squared, which is 169, minus 4 times 3 times 11 all over 6. So that looks like it's going to be 13 divided by 6 plus or minus 169 minus, what would that be, 121 plus another 11, 132. 169 minus 132,
37.
Yeah.
137?
No, 132.
Oh, okay, 132.
Yeah.
All right. Or
I know the answer is subtraction.
Oh.
13/6 plus or minus the square root of 37 over 6. Well, the square root of 37 is a little bit over 6. So both of those answers are positive. Would you agree?
Yeah.
Okay.
Oh,
so-
okay. Yeah. I got
Okay, and so on my
Yeah.
timeline, or here's t equals 0, I've got some number which is like 13/6 minus square root of 37 over 6, and over here I have 13/6 plus the square root of 37 over 6.
Okay.
I'm only interested in the time when time is positive.
So they're both positive.
Wait, so why are we...
Yeah.
I'm confused.
Yeah.
Okay.
It's like a step there. So 4 times 3 is 12, right? Times 1 is it times 11?
Times 11, yeah. That's 11 there. All right. Okay, so here's what I know. For t that's really, really big in my velocity equation, that's a big positive number. Velocity is positive after that second root. There's a sign change here,
Oh, okay.
and then there's a positive. So I might say, oh, this particle is moving to the right from 0 to whatever that number is. It is moving to the left on this interval. And then once we get past the second root, it starts moving to the right again. Let me summarize.
Oh, I don't remember.
It's moving to the right from 0 to 13.6 minus root 37 over 6. It's also moving to the right from 13.6 plus root 37 over 6 to infinity. The particle is moving to the left when it has negative velocity, which is on the interval from 13.6 minus root 37 over 6 to 13.6 plus root 37 over 6. And that's all part A. Was that grand?
Dandy. Wait, when is it? Oh, I got you.
You got me?
Oh, yeah. I got you.
Yeah,
Everyone okay with that so far?
Yeah.
No.
No. Where did I lose you?
I mean, I understand the plus, minus, plus up at the top, but
So you're okay here.
yeah. The right and the left, that's
Okay.
the part.
This is that the particle moves to the right. When velocity is positive, the particle is moving
Oh, okay, we're talking about on the graph. Okay.
on the graph.
Got it.
And then the particle is moving to the left only in the spot where the
Negative.
velocity is
Oh,
negative.
Yeah.
So we're good there?
Yeah.
So that's part A. When does the particle speed up? When does the particle
We have to take the
Slow
double
down.
derivative of position or the single derivative of velocity to get the acceleration equation with respect to time, and then you figure out, you do pretty much the same thing, but just with the acceleration.
Okay, we say that the, no, this is the tough part of this all. Okay,
Notation.
well, yes, we have to look at acceleration. Are you ready to do the speed up, slow down part? Because it's something that we really didn't cover in class. You ready? So I'm going to leave the velocity function up here. And I'm going to leave this timeline up here, but I gotta get rid of everything else to do this next part. So if you don't mind, I'm going to erase all of this. All right. Now let's take a look at acceleration. The acceleration of this particle is going to be equal to 12t minus 26.
Oh, you have to just find out when that equation is positive and when it's negative.
No, it's not that simple. I wish it was.
Sorry?
Okay. All right. Are you okay with that idea? Okay. So we easily can find acceleration. All right. Now, when is something speeding up?
When it's
When it's
acceleration.
positive.
When the
Whenever it
acceleration is
moves.
positive? No. And that's a big problem. This is the biggest problem. Okay.
Acceleration.
I'm going to demonstrate
Oh, I
using.
get it, I get it.
Let me explain it though. Okay. Here is a pen. I throw it in the air.
Maximum.
When was it speeding up? Was it speeding up on the way up?
No.
Yes.
No.
No.
No. As I'm throwing it up, the velocity is constantly getting smaller to the point when the velocity is equal to
Zero.
0.
Yeah, so
And then as it starts its downward path,
it speeds up
It's accelerating.
then it speeds up.
decreasing.
Okay, ready? Now, so can you use a rule like when acceleration is positive, that's when it's speeding up?
No.
No, because in the situation where I throw this up in the air, acceleration is constant. Remember? Negative 32 feet per second squared or negative 9.8 meters per second squared. During this entire route, the acceleration is constant. Particles speed up when the acceleration and the velocity are of the same sign. When this pen is going downward, it has a negative velocity.
Yeah.
And acceleration is negative as well.
Okay.
And thing speeds up when its acceleration and velocity are of the same sign. So when I toss it in the air, it has positive velocity, but it's got negative acceleration.
So positive.
So something slows down when velocity and acceleration are in two different directions.
Yeah, then it's negative.
Okay? So we got to take those two things into account. The direction of the velocity and the direction of the acceleration in order to answer the question, when does the particle speed up? Ready? Here is acceleration. Okay? When is acceleration 0?
Uh,
26 divided by 12 is t. I might make a timeline for acceleration. And I might put, what would that be, 13/6?
yeah,
And when t is pretty big, acceleration is positive, and when t is relatively small, acceleration is negative. Right?
Why?
Well, when I'm looking at the acceleration function, I know that there's a 0 at 13/6, and then I just say, everything after 13/6 is either going to be all positive or all negative. And I just imagine putting a really big number in there. And when I put a really big number in there, what happens?
it's
A big positive number. And on the other side, since this is a single root, the other side has to be a negative. Okay.
so then it's speeding up.
Okay, well, let me, if you will, I just want to draw that 13/6 line right there. Remember, velocity is here, acceleration is here, and all the way over here, or on this side of that red line, it's all negative. And on this side of the red line, oops, put that down here. This is all acceleration, and this is acceleration. So you ready? It's speeding up when when acceleration and velocity are the same side, and that's going to be on the interval from negative, or from 13/6 minus root 37/6 all the way up to 13/6. This is speeding up because the signs of acceleration and velocity are the same. And then it's going to be speeding up from 13/6 plus root 37/6 to infinity. Because in that area, acceleration and velocity are in the same direction. When is it slowing down? And why isn't it speeding down? And why isn't it slowing up? I don't know. All right. When is it slowing down? When acceleration and velocity are opposite signs. So from 0 to 13/6 minus root 37/6, and then also from 13/6 to
Root 37 or 13.
to 13/6 plus root 37/6. And all of these are in seconds. Hey, we're all the way through B now.
Wow.
And there's F all the way through. Like,
No, actually, from here on out, it's pretty easy.
Yeah.
Because we have the two number lines.
Well, because we have the two number lines. When does the particle change direction?
When velocity
13
becomes
over
10
6 minus 13 6 minus.
Sure.
What can't we just say 13 over 6 plus or minus root 37 over 6?
Yeah, we could probably see that.
Save paper, save the earth.
Okay. So in C, it's going to be, as Mr. Duchesne wants to put it, it's 13 6 plus or minus root 37 6 seconds. That's when it changes. That's when it changes direction. And you can see that they wrote it down in decimal form. It's fine. Okay. When is the particle at rest? At the same places.
Yeah.
Because the only place it can change direction is if it goes to 0 first.
So C and D.
So C and D, you can see it has the same
Okay.
answers. Right? Describe the velocity and the speed of the particle. Well, I've described the velocity in this function right there. What's the difference between that and its speed?
It's the absolute value. So the absolute value of that equation.
Okay, so in what is this, E? In E, I might say that the speed is equal to the absolute value of 6t squared minus 26t plus 22.
Do you want us to simplify that to change to the sign in the middle, or just like
No,
it's fine?
that's fine the way it is.
Alright.
And then all we're doing is worrying about the last part. When is the particle at the position 5.2?
When it's at 5. Because it's always
When x is 5.
Yeah.
Okay, are you ready for me to erase all the stuff that we have so far so we can finish
Yeah.
this last one? Are we? Okay. Here we go. Tough erasing all this. Alright. So the last part is when does
When does
x
equal 5?
Alright, so x of t is equal to this mess minus 13t squared plus 22t minus 5. And we want to know when is that actually equal to 5. You know what I do for this?
You put 0 on one side and add 5. No.
Oh, yeah, no. I can add 5 to both sides, but I don't think I can factor that very well. I don't think it's factorable.
So
Well, if you
graph
added
it,
the 5 and then
graph
pulled
it,
out a t,
You
graph
can't get rid of the 5.
why can't you get rid of the 5? Because
it. You can add
I mean,
5.
if you add 5 to both sides, you would
I
get rid
get
of 5 on both sides.
Well, if I add 5 to both sides,
You get 10.
I get 10,
So
and
you
that doesn't make
Oh,
that
that's
easier to
subtract
solve.
5. Oh,
So-
yeah, you're right.
Right. So,
graph it.
so in this instance,
The graphing
although I've been
calculator.
avoiding using it, we really need to go to our graphing calculator to finish off the job. There are certain things that the AP exam writers expect you to be able to do in the calculator. Finding roots of an equation is one of them.
So wait, how do you change x to t?
Okay. So we see our equation, and my tendency is to want to put was it cubed minus 13t squared plus 22t plus 5
Minus 5.
minus 5. Okay, so there's my position equation in y1. And here I am trying to find out when does that equation equal 5. And now I'm going to graph them simultaneously. All right.
3 different places. Wow.
So we see that these two curves intersect in 3 different places. So
Second
the
time.
curve is the position, And now we're gonna ask the question, well, what are the values of t that cause that to happen? I think it's under second calc. I'm looking for an intersection, which is option 5. I have to choose which are my curves. There's my first curve, there's my second curve, and then I gotta put in a guess.
Wait,
about there.
what's first curve, second curve?
Well, because you can have more than 2 curves on your graphing window at the same time,
Oh, you have to choose which.
you have to choose which 2 curves you're looking for the intersection of. And then you have to put in an approximate guess of which intersection you want. So there's one intersection, looks to be about 0.745 seconds. And now I gotta find those 2 other intersections. Again, second calc, intersection, first curve, enter, second curve, enter, and then I'm gonna scoot over so I can get closer to that other intersection point. So it'll find that intersection point at approximately 1.626 seconds.
Here's the calc button.
Calc button is second trace.
And then the last one.
And then the last one, second calc, intersection, first curve, second curve, and then I gotta get over here to where that, closer to that last intersection. There we go, enter. And then it looks like the last intersection is approximately 4.130 seconds. No, 4.129 seconds. And that's problem 37 in all its joyousness. Joyousness?
I think the word is jollity.
Because on your
Sure.
earlier computer, you were doing parametrics, I was like doing like an order from the line.
Really?
Yeah.
Yeah, this is much easier than I think I just did it better than I did last time.
But it looked cool. Like the
Oh.
dot was moving. Like,
Oh, yeah. I mean, I can actually show the dot moving parametrically.
and
So-
everyone was like,
Would you like to see that? If you didn't watch the recording?
Sure.
Sure? Well, it's just that, it's, you know, when we looked at this graph, this graph is moving in the y direction, but really the particle is moving in the x direction. Well, I can actually model, using parametric mode, I can actually model the movement of this particle by putting the t equation, the position equation for the particle into x1 equals,
How did you get to x1?
well, you gotta go into mode and change your mode from function mode to parametric mode.
oh yeah.
Parametric, love those guys. Because then you can see the little ball go left and right.
Right? And so here I am putting
Oh.
the equation for x into x, and then the equation for y is just the value 2. Because we said the particle is always at y equals 2. And I'm going to go over here. Come on, get over. Go up and over. And then I'm going to change my line to have the little
Ball.
football on it.
Why?
Well, that way, when I graph it,
It looks like
you can see the particle moving. I don't know if you saw that. Let me.
yeah.
Okay, so you put in the position equation, right?
I put the position equation for x into the x equals, and again, y was constantly a 2, so I put 2 in for the y. And then when I graph it, you can see there's the particle. It starts way over, sort of to the left-hand side. It's moving to the right. Oh, here's that first turnaround point at 13.6 minus root 37 over 6.
I think I messed mine
And
up.
now it starts moving to the left. And then how long is it going to continue to do that? No, until it meets that second turnaround spot where velocity is equal to 0. I slowed it down for you so you can see it.
Check it out.
then eventually it's going to be time is equal to 13/6 plus root 37/6. And now it moves to the right again. And how long does it continue moving to the right? Forever.
Forever and
I
ever
did
and
something wrong
ever.
Mine keeps saying invalid gem online. I don't know why.
Because you got this block turned on. You
Oh.
need data for it.
Okay.
All right. So have we handled that well enough then?
It's still not.
Yeah.
I still,
I know.
Okay, I'm gonna cut off the recording and then we're gonna take care of your calculator problem, Jim.